I mean, I took stats in high school. So.
All right. So today we're going to talk about the follow-on from the last lecture, which is the use of binders and polymers in ceramic injection molding. And so this is where these issues of things that material science people don't always care about very much come into play. But if you're put in charge of a process and you're responsible for the success or failure or the cost per part resulting from that process, then all these things become very important to you. So we're just going to talk about that from the context of trying to make parts. And as you guys all know, this is upstream from the actual sintering process, but this is going to impact the sintering process itself because it determines how much space exists between the particles and therefore how much space and carbon may need to be removed from those particles. But so all these things are kind of mushed together in terms of making this process successful or not. And so, as I think I mentioned last time, ceramic injection molding was, people were jealous of the plastics industry in the 60s, and they said, hey, let's try to do this, and they spent 20 years at least trying to make it work, and where you guys are going to see the end game for that whole process of making it work. And so it's quite complex, and it touches on a lot of stuff involving polymers, and so we'll discuss some of those aspects as well when we come to them. And so polymer selection in these systems, can they turn the music down over there, whatever that is? Is that a video next door? Okay. I got a guitar backing my lecture today. Polymer selection is important to us, and in this particular field, where they talk about binders, and that's what it says here, that these binders are going to be a total collection of polymers within a system. And so there's binders, plasticizers, lubricants. A lot of these things are talked about as if they have one specific function in these batches that we're going to be discussing. But in reality, they tend to be a soup of organics, and so they all act kind of in concert with each other. So sometimes it's not honest to say, oh, it's just a plasticizer, because it affects everything else in there along with the rest of the soup. So, but anyway, we talk about binders being the polymer that occupies the space between the particles, and then after everything's created into this total knee, for example, this is what helps hold it together. And it's important because what it does as you heat it up to remove it, that can be a problem. If it doesn't keep holding it together and gravity can cause a part to slump, then that total knee will change shape and you just pitch it because it's not worth machining back to its original shape. It's the 1960s now. All right. So because the system is complex and consists of more than one polymer, it is often difficult to clearly identify the role of individual binder agreements. However, that doesn't keep us from applying labels. All right. So binders, plasticizers, and various processing aids. And so we'll go over some of those things today. I mean, it's going into this, it's easy to say, oh, categories. Here's what they do, and they don't do anything else. But in reality, they all tend to work together. So keep that in mind. Very distracting. All right, we will introduce and discuss the various polymer materials used in ceramic injection molding. It's always nice when a class consists of standing in the back and letting the movie play. Proportions of these additives, their effects on viscosity and flow when combined with ceramic powders are critical. And a lot of this has to do with getting things to integrate. And so today we'll talk about polyethylene as a binder, but you take polyethylene by itself, you can put it on top of alumina, and if you heat it up and melt the polyethylene, it'll roll up into a ball on top of that alumina. It does not like alumina. And so what we have to do to get it to work for us is try to condition the interface so that we can get the polyethylene to like the alumina and work with it in making these batches. Proportions of these additives, their effects on viscosity and flow when combined with these products are critical. So this issue of flow, we need to get it to go into the die. The die has nooks and crannies. It needs to fill those spaces efficiently. All those things are important to us making parts that are successful. And as always, avoiding defects remains paramount. And so I think I mentioned this last time, if you don't control the process, you can create defects. You can cause defects like a polymer-rich area to occur. And that means when you burn it all off, it's a big old defect inside that part. So, this is where things can go horribly wrong. Void-free, stress-free, uniformly dense molded shapes are still the ideal goal. And general selection guidelines have been developed, but a lot of it's process and error, or trial and error, involving the process. And so, as you'll see at the end, they work with these ternary diagrams, and those are all painfully determined by a process and error. No one models these systems because they're just too complicated to model. But we do have some general goals here. Binders that are hygroscopic cannot be considered. What does hygroscopic mean? Anybody? Nobody took a meteorology class or anything? Hygroscopic? No? All right, hygroscopic is like salt. It likes water a lot. So you take salt and you put it out on a table and increase the humidity to 95%. That salt will turn into a puddle on top of the table because it sucks water right out of the air. All right, it really likes water. And so we don't want to have that in this context because of why? Why would that be a problem for us in terms of our injection molded part? It sucked water out of the air. So when we take that part and put it into a furnace, the water's got to come back out, right? As part of that heating up process. And if there's enough of it, it can blow the thing apart, which is unlikely. But still, you've got something that's taking up space and needs to be removed and can compromise the strength of your part. All right, it becomes a very delicate balance. We also don't want binders that are volatile. What does volatile mean? At least room temperature volatile. Yes? Easily evaporated, right. So we don't want something that evaporates at room temperature. We'll talk later about how we actually get it to come out, and that involves making it volatile at much higher temperatures, but we don't want something that generates gas when we don't want it to. Excessive migration will disqualify a binder because it can lead to skin effects, delamination, and crazing on molded parts. So those of you who are refugees from polymers will remember crazing, all right, and that's if you have enough polymer sitting there by itself and you put mechanical stresses on it, it can craze, which can lead to issues as well. So we don't want binders that move around a lot because they'll tend to concentrate, and that's a problem. Mechanical properties are important. A weak, low-stress polymer will flow well, but a too weak polymer can lead to part distortion during binder removal. This is sort of the yin and the yang part of this, is that you want something that works great rheologically and gives you the flow properties you want, but then you have to turn around and heat it up and remove it. And if that nice low melting or easily flowing polymer is sitting there in a furnace at 300 degrees and it starts to melt and flow, well, your part's going to start to melt and flow. And that is a very bad thing because you're changing its shape. It's no longer a total knee at that point. And so this is the game you have to play primarily with molecular weight and material selection to try to make sure you have something that you can be made, gives you the shape you want, but then in the heat up cycle where you need to remove that polymer doesn't the shape of the properties of what it is you're making. And so in general, everything together, this soup of different polymers, you want it to give you a viscous melt upon heating to above the glass transition. Let's see, some of you know what a glass transition is. Are people reasonably comfortable with what glass transition is? I hear about with glasses, but this is not really an inorganic glass. So glass transition is the temperature at which polymers become soft. Okay, and so if you take a polymer and put in liquid nitrogen and drop it on the floor, most times it will shatter. All right, that's because it's below its glass transition. And so what we're doing in this context is we're heating things up and getting them to flow. And it requires that they not be brittle, and that's the glass transition. We go into a lot more of it with the polymers, guys, but that's the gist of it. High viscosity is necessary to retain the powder in whatever degree of dispersion or deagglomeration it possesses following the green state. And so we, unfortunately, are stuck with high viscosity polymers. We can't use just like floor wax, low molecular weight paraffin or polyethylene. We have to make it high enough molecular weight that it's got the right type of strength and also gets in between the particles. And so last time we talked about various things. Brownian motion, slamming particles together, causing them to fall into the energy well and get stuck. all right? But now, what this refers to is the fact that if we have polymers in that system, the polymers get in the way, and they keep them from getting close enough together to be stuck in that hard energy well. Because these are high molecular weight materials, if Brownian motion drives two particles together, it's not enough to push the polymer out of the way, all right? Water maybe, or hexane sure, but not a high molecular weight polymer compound. So they're really important in this context. We also have something called curing time. And what curing time refers to is if you go to the grocery store and you buy a 5-minute epoxy and bring it home and put the two pieces together and then mix it and hold something together, there's a curing time, which involves those two components reacting with each other and before it becomes a hard epoxy. Or if we're working with a PDMS resin and we're trying to make biosensors that are insensitive to the components of the environment by putting PDMS coatings on nanofibers, all right, that's the same thing. It's a two-part resin, and they need to react with each other in order to polymerize to give you the right type of structure. They also need to have a long shelf life, so the polycaprolactone we use in the lab, we had that bag for 10 years now or something like that. So it's still good. We still use it. We're not too worried about it because it doesn't break down. You want to make sure that if something you buy ends up in a corner for a while, it maintains its properties. Good strength after molding. And again, so this is the next step beyond you have to think about here, because you put it in the furnace and heat it up, and you don't want it slumping because of low strength. And something we'll talk about a lot later is minimum carbon residue, which is very important for CIM, because when you take carbon, you put it into a ceramic microstructure, then that carbon is trapped there basically. All right, it's between two grains, it's carbon, the alumina or whatever it is doesn't bond to it at all. That's a huge flaw in your microstructure, an enormous flaw. It makes it very weak. And everything else is subservient to the fact that it also has to be low cost. Right? We can't have really expensive polymers in the system, especially since we're going to turn around and burn them up or chemically break down, one of the two. And so flow into these cavities is governed by the viscosity. Oops. And we all know what viscosity is, right? Sometimes people aren't properly oriented. This table is a very high viscosity. Air is a very low viscosity, okay? Make sure I get that. Some people flip that around for some reason. And when we talk about flowing into these cavities, you guys have seen the shape you're creating, but there's a gate that goes into that cavity, and that gate's pretty tiny. It needs to be tiny, all right? And so viscosity governs how easily that flow can go in through that tiny little gate. And what we often do is use shear in these processes. And so this is something we're going to do a lot. I think the biomedical guys, you have homogenizers, which are based on shear. And those are used to break tissue up into soup, basically. You drop your finger in there and it turns it into soup in 2 minutes or something like that. So that's done by shear, which means that two surfaces are moving past each other very quickly, and that breaks things down. And in this context, it breaks down molecular interactions that arise from entanglements of different polymer chains, both inter and intramolecular, meaning between different polymers and between itself, and that's necessary to help mix things together. You can't have a big hunk of polyethylene and a bunch of alumina separated from each other. You got to mix them together, and that mixing has to be very intimate, all right, as you'll see. And so these behaviors are unsurprisingly controlled by molecular weight and the molecular weight distribution of these additives. And just to make sure we're on the same page there, I know some of us are already here, but if we look at the molecular weight of a polymer, doesn't matter what it is, polycaprolactone, I talked about it a minute ago, whatever makes this desk material, it's not one molecular weight. There are different chain lengths. So it's always a range, and we often characterize it with some type of average number like a molecular M sub W or N sub N, depending on the technique. And we think about it this way, and it's a nice Gaussian curve, but we can have other things that happen. We can have a curve that is much more interesting looking, that has high and low peaks in it. All right. We analyze this with our technique. We get the same weight average molecular weight, which says that the green and the yellow polymer have the same molecular weight, but in reality, the yellow polymer has these things out there. And as you'll see, this low molecular weight species especially can affect the overall behavior. All right, and so we can't just rely on one number to characterize these things. So keep that in mind. Molecular weight is a distribution. And then we also, we characterize these things by determining the viscosity, both as a function of shear, meaning that we shear the heck out of it with these mixing systems, and I'll give you a video of that here, I think the next lecture, and as a function of temperature, including the melt elasticity. So we want to know how much shear is necessary to establish a certain viscosity, and we also want to know what happens to that as we heat it up, which is also part of the injection molding process. So we start at room temperature, not high enough temperature to make polymer melts. We have to go to high temperatures like 200 degrees, and we form the object, and then we take it out and we put it into a furnace and burn away the polymer. But this is all part of how we establish how well a material is going to behave. All these are important in determining optimal processing conditions, the equipment, which can be pretty pricey, especially if you're doing things at scale, as well as the maximum speed of the processes. Of course, that's the thing that we never talk about in material science, is the fact that our boss wants to make these things as fast as he possibly can. All right, so there's that pressure to get things done quickly rather than the most efficient way, all right, or the most rate-controlled way. There's always this push to make things more quickly, and that's part of this. And we describe the shear behavior in terms of flow characteristics exhibited by these various systems. And so there's a whole bunch of things out there, a whole bunch of different systems out there, and we'll talk about a few of them today, but there's just hundreds of different polymer ceramic combinations that can be injected that people have looked at. And one of the way of describing these things once we're done, so we've somehow, with a shear and a lot of other efforts that we haven't talked about yet, produced a homogeneous batch consisting of a ceramic inside a polymer, and that polymer is a melt, which is different what we talked about before. And so I'm skipping ahead a little bit because this is the state of the art as far as injection molding of these ceramic components is concerned. And so we produce this blend, and we have different ways of thinking about the viscosity. And first off, there's one thing that you should know about, which is 0 point of shear. What does that mean? It's a fancy word for saying we take these curves of viscosity versus shear rate and extrapolate them back to 0 shear rate. And this is where you get these numbers, ZPS or ZPC, where you have this extrapolated viscosity value if the shear rate was 0, which is crap because it doesn't make sense, but it is a common way of referring to how these things behave. And if we look at the behavior of these batches versus shear rate, all right, remember I said shear is really important, and this is an example because they're plotting this behavior to see how hard they have to work to shear this stuff. And what we're all familiar with is Newtonian fluids, because water is the one that surrounds us every day, and water is wonderful that no matter how quickly you shear it, it always has the same viscosity. All right, that's the great thing about water, at least in terms of materials. Physicists can make it do other things, but as far as we're concerned, it has a fully 0 slope in this context. So that's good. But the batches we're talking about, with ceramic and polymers together, don't behave like a Newtonian fluid. All right. They have a couple of different choices. As you increase the shear rate, you have the dilatant behavior, in which you see the viscosity go up. And then conversely, these other Bingham plastic, St. Bennett body, pseudoplastic, you see the shear rate, as the viscosity goes down, the shear rate goes up. All right. And so this is giving us some idea of eta, all right, which I've drawn here. And as eta goes up, we have to work harder, right? It gets thicker. It means we put more energy into it. We make things go faster. Not always a good thing. And so what we'll talk about in just a second is the fact that these behaviors are governed by structures that develop inside of these liquids, all right? And so they're not gray, homogeneous liquids that are the same everywhere, but they actually have individual structures inside of them that cause this behavior to occur. And that's why we concern ourselves with it. And it's very important in terms of processing. One example I always like to give is that, I don't know if this is anecdotal or not. It'd be great if somebody could find me a YouTube video, but there's supposedly there was some plant where they're manufacturing a pseudoplastic batch, and they have these 1,000-gallon drums of this stuff because they're making a whole bunch of it. So like this is the rim of the tank, and it goes all the way around the room, and it's filled with this 1,000-gallon white batch of a pseudoplastic material. And the story goes that if it was sitting there and it wasn't being stirred, that you could walk out on top of the batch because it had a high enough viscosity at low shear rate that you could literally, it would support your weight. But the trick was you couldn't walk fast, because if you walked fast, you'd increase the shear rate and boom, you go under the surface of the batch. I don't know if that's true or not, but that story's been around for a while, so it's probably true. But this is just an example of what happens as a function of viscosity versus shear rate. And yeah, again, if anyone finds that on YouTube, let me know. But that just gives you an idea of how quickly these properties can change as a function of shear rate. All right, any questions about that? I know this is new stuff, or at least maybe in Jose Castro's class he talks about this. I don't know. Or not. Those systems are simpler. All right, so we just talked about this already. Newtonian flow, constant. St. Venant flow, Bingham flow, pseudoplastic flow. We see viscosity decrease with shear rate. And then the converse case, dilatant, the viscosity increases with shear rate. And so what we have in both cases is structures that exist that break down in one case, and then in the other case they can grow. All right, and we're going to talk about those structures. And the thixotropic is also another example of this behavior. And so the kind of structures I'm talking about consist of, let's say we have alumina particles, and this should make some intuitive sense. If those alumina particles all line up and form a string inside this, all right? So versus one individual particle by itself, it's going to be harder to make that string move versus a single particle, because that string has greater mass. You've got these forces holding these particles together, some of which we talked about. And so what this can then do is increase that viscosity versus a single particle by itself. Okay, so hopefully that makes sense. We can also have different structures that consist of strings of particles connected by other particles. All right, so sort of a cellular, almost biological type structure. And so this can get pretty complex. And so this gives you an idea of why when we shear this, the viscosity can go up. If these structures form, if you start tearing these things apart, the viscosity can go down. All right. And so because we have these ceramic particles in there, surrounded by polymer, but these ceramic particles can make these different types of structures inside of this melt. Any questions about that? Hopefully that makes some sense. And so this exhibits power law behavior, range between Newtonian and pseudoplastic dilatant, depending how they're formulated, and this follows a power law relationship, tau being equal to constant K times the shear rate taken to the power of n, where K is a consistency coefficient, basically a fudge factor that makes your relationship work, relating to the flow of a real fluid, okay? And then n is the power law exponent, tau is the shear stress, and gamma dot is the shear rate. And shear rate is how hard you have to work to make this thing become a homogeneous melt. And so this shear stress obviously scales very sensitively with the shear rate, all right? The amount of work you have to do is very sensitive to that. And in terms of doing practical things with this, what we will typically do is just take the base 10 log of tau, which is equal to the base 10 log of kappa, or K, that's supposed to be a 10, plus n times log base 10 of the shear rate. All right. And so those of you who may have done something like this in the lab would know that we would extrapolate and figure out what the slope of a line is based on experimental data. And that's how we'd get n from this relationship, is by breaking it down into the log-based equivalent form. So anyway, that's the governing relationship here, where we have a certain type of shear stress that's required, and that translates to a certain type of shear rate in these systems. And then n, of course, is going to be very important to us because it determines how hard we have to work. Any questions about that? And so what we see is, as a result of this, is a log-log plot of shear stress versus shear rate. Newtonian, talked about, slope of 1, dilatant, greater than 1, all right, meaning that it becomes more difficult as we increase the shear rate. And then the others, the less than 1 slopes. And then fluid behavior that does not obey specific power law relationships is usually represented by a curve, which can go back and forth between the different regions depending on the structures involved. But this gives you an idea of what we have to do and how the log of the shear stress, which you can think of this in terms of money. How much money do I have to spend on my process? All right, if I go to higher shear rates, that means more money, more equipment. Higher shear rates, more energy. And so there's a direct translation between where you are in this curve and how expensive your process is. Okay, so processing aids then are part of this. And this harks back to these structures. And how do we get to these structures? And so I've kind of segued into the idea of this melt in which the ceramic particles are kind of dispersed. But there's other things at work here, and that involves what type of bonds exist. So if I go back to that one example of these particulates held together by other particulates, and I start to try to shear this thing, all right, we can look at this in a couple of different ways. First thing that would break under shear are the bonds that hold these two chains together, because it's easiest to do. All right, that should make some sense. And then afterwards, if we keep shearing it, we want to break down our viscosity, then we start breaking these bonds, the ones that exist between the linear structures themselves. And so all of these are controlled by how much do these particles like each other at these interfaces. What determines the magnitude of the red X? What determines the magnitude of the blue X? How strong is that attraction? And this is also governed by something happening at a very small scale. And so if we stick with alumina, and this could be aluminum metal for that matter, because aluminum metal has oxide on the surfaces, and it behaves exactly the same when you put these into solution. So we know from what we talked about before that alumina is going to have a layer of water on it, because that's what these things do to minimize their surface energy. The first thing they do is form a layer of water, and it can be a monolayer at the very least, but more likely it's a multi-layer of water sitting on those surfaces. And so we have this issue in that those surfaces have an attraction to each other. All right, so they're both hydrophilic, and we have, if you recall, we have Brownian motion trying to slam these two guys together, and when they get really close together, they can bond very tightly. All right, and so the way we get around this is by producing what's called, you might want to think of it as a hairy layer, but we think about this as polymers that are attached to these particles. And the key here is that these processing aids are not attached in the melt process. And you remember that complex diagram I showed you that had all the different pieces of this overall process. This is way back at the beginning. So we attach these processing aids at the very beginning of the process to produce these layers. Okay? And these are very important and that it keeps these guys from approaching too closely to each other and falling into that energy well and getting stuck. All right. And so we've talked about agglomeration. You guys have an idea what that is. It is something that is inevitable, as you can see from these structures here. You always have some type of agglomeration forming, but in the context of these polymer melts, there's a difference between what's called hard agglomeration and soft agglomeration. Okay, hard agglomeration is the nightmare scenario where the two particle surfaces actually touch each other and they're deep into the energy well, and it takes a lot of mechanical force to pull them out. Soft agglomeration is what we've done here, where we take polymers and we force them to exist in between those two particles, meaning that they can get kind of close together, but not all the way, because the polymer's in the way. All right. At the very least, we have processing aids in the way, and then in these real practical situations, we also have other types of polymers here, whatever it might be, whatever constitutes our batch, is also in the way. All right, but we still get some agglomerates, but they're separated by a minimum amount of polymer, and so the forces that hold them together are not that strong. All right. Yes?
So do you still need energy to break them apart, but just not as much?
Nowhere near as much. Yeah, it's much, much easier. We also don't, because they're not big hard agglomerates, the consequences of that are much more minor. So if I have a hard agglomerate, it's a bunch of particles all stuck together, that's likely to form a defect. Mm-hmm. That's the issue. All right. These soft agglomerates, when they do form, they can be easily deformed. They form more coherent structures, and the defects involved are much, much smaller. Okay. But at a minimum, we start with the processing aids, and then we ideally get them to go into the polymer as well. So these processing aids, let's just go to this one. These are additives that affect the performance of the overall batch by modifying the cohesive forces, the ones that would try to pull these particles together, between the surrounding polymer and the ceramic powder. All right, so remember back at the beginning I talked about polyethylene and how it hates alumina and vice versa. This is how we modify this, using these processing additives. So if we have, again, let's just make it black this time. We have alumina, and we have water on the surface of the alumina. All right. What we can now do, in order to produce those yellow lines I showed you before, in the previous class we talked about this, we can have this carboxylate group. All right, so that's carbon double bonded to oxygen and also bonded to OH. That is not a very good drawing. Do it this way. All right. And so that's a carboxylate, and it's got hydrophilic groups on it, which will attract it to the water. All right, so we're good there. And this happens normally anyway. Just crap in the air will do this as well. We talked about that before. But the advantage we have here is this fourth bond to carbon. We can make this a polyethylene chain, literally. I'm going to talk about oleic acid and stearic acid in a minute, and that's what these are. These are carboxylate groups with 18 and 22 length polyethylene chains sticking on them. Okay? And so the beauty of this is we get something that adheres to the surface, all right, and then carries with a polyethylene. All right? And this is where the tail that comes off the surface of those particles comes in. Those tails come off the surface, and they get in the way of the particles getting close to each other. Okay? And so this is where these are processing aids. We talk about, like I said, oleic and stearic. Those are processing additives, and this is all that they do. And this is a very trivial layer. This is not something you can turn around and put into a melt by itself. It needs to have a lot of other polymers around it. But that thin layer sitting on top of these ceramic particles plays a huge role in the success or failure of the overall process. Okay, how's this going to go? Yeah, some parts of the drawing move and other parts don't. Okay, and so this is very critical to the performance and the efficiency, and that's why it has its own step way back at the beginning of the process. All right, its own step well, it's putting these aids on it, taking the powder, drying it out, and then throwing it into some type of polymer-based batch. But without these aids, ceramic dispersion or elimination of agglomeration would not be possible. All right, regardless of how much shear you throw at it, the polymers aren't going to do this on their own. You need these additives and that type of chemistry to get to the goal. If you don't, you have flow instabilities, inhomogeneous microstructures, critical flaws, of course, the death-dealing thing, involving sintering. You might think that all you need to do is just throw energy at it. You could shear the heck out of this stuff, and that will destroy agglomerates. But if you don't have these things in the way, they spontaneously reform. So you spend all this time, you pull them out of the energy well, huge amounts of energy, and then they go pow right back into the energy well because there's nothing to stop them. All right, those surface forces there, van der Waals forces, hydrogen bonding, that's all still there, and it'll just pull them right back together again, unless you put something permanently in the way, and that's what these processing additives do, is they sit permanently in the way, make sure and keep that from occurring. How do they do this? So as you know, attraction between particles results from van der Waals forces, including London forces, and hydrogen bonding, especially hydrogen bonding, very strong, and will otherwise, especially when they get jammed into each other using Brownian motion, they'll stay stuck together. With ceramic injection molding, we minimize this by steric hindrance or entropic repulsion between polymer chains adsorbed onto the particle surfaces. And so this is an example of that. So if you went back to my other cartoon, these are those yellow chains coming off the surface, all right? They look like hairy polymer layers. That's what people call them, actually, in the literature, hairy polymer layers. And so these layers are sitting there, and these particles, driven by Brownian motion, are trying to be pushed together, and those polymer layers are there. And what happens if you have enough energy is the polymer layers start to overlap because you're driving them together, all right? And as you take polymers and you drive them into a structure, you reduce the number of available energy configurations, which means that what happens? Some polymer refugees want to try to answer that one. You guys don't remember? So we reduce the number of available entropic configurations available to a polymer, all right? And then the energy of the system goes up because polymers don't like that. They like to be as random as possible. And what you're doing here is you're packing them together and you're taking away some of that randomness, all right? So what happens is we have this entropic barrier that is generated when you try to drive these two polymer coated particles close together. All right, so what that does then is it pushes them back when that overlap occurs. All right, so entropy wins one more time in this context, but entropy wins for us in a way that allows us to maintain separation between these particles. But it's not, there's still some attraction going on, don't get me wrong. These surfaces are still attracted to each other, but they can't get close, all right? Is that clear? They can't get close enough to fall into that nasty energy well. It also reduces the interfacial energy between the binder and the powder, meaning that we can get wetting. Meaning that if we have a polyethylene chain, then we have the ability to have these polymers interact with a polyethylene melt around them. That's the other aspect of this. It's also very important. If it's sitting there in polyethylene, those chains will interface and solubilize in polyethylene. And that gets us to where we need to go as far as a homogeneous melt. I'm spending too much time on this stuff. So processing aids. Compatibility is achieved by adding small amounts of processing aids, wetting agent, coupling agent, some combination. Usually contains both polar, and you saw this, the carboxylate, and non-polar, the polyethylene, moieties. And we talk about having a polar head and a non-polar tail. And these are some examples of very widely used processing aids. So oleic acid, stearic acid are both derived from plants, which means that they're really cheap, all right? And they're exactly what I drew you a cartoon of. It's carboxylate on one end and then a naturally produced polyethylene chain coming off of that. So we just produce these from plants. There's also oxidized Menhaden fish oil. So again, something that's cheap that somebody else would rather throw away, but you can use it as a processing additive here. It's necessary to oxidize it because Menhaden fish oil, without being oxidized, will clear the room. The stuff stinks to high hell. You oxidize it and it's like, yeah, it's okay. But anyway, so these are the kinds of things that are used, and they all have the same type of theme. They have this ability to attract to the surface and then provide a polymer. And I mentioned coupling agents. Some of you have seen this before, but these are silanes or titanates, and they chemically adsorb or bond to the surfaces. They don't just have an attraction to it, they actually chemically adsorb to it. And this is just, I'll just pick this middle one, where you have this SaOH, and you have some type of ceramic, and you end up forming a bond that includes the metal oxide that makes up that surface. All right, and so we have a permanent chemical bond that helps keep these things on the surface and change the processing behavior in a favorable way. And you might think these are kind of obscure, but they have entire books about coupling agents out there. They have conferences where people get together and talk about coupling agents. And so this is a measure of how important it is to this area, that if you didn't have these types of chemical technologies, the field might not exist. Okay, and so what do these things do besides keep the particles from agglomerating? They also have very pronounced effects on viscosity. And these are some examples. As you can see, the effect of silane and titanate coupling agents, meaning that they react with the surface, on the viscosity of a mix containing silicon nitride, all right, and polyethylene binder. All right, so high-tech ceramic with polyethylene that is sitting in between the particles, and they take this stuff. I'll just use this first graph. We have untreated silicon nitride particles, and what you're looking at is viscosity versus shear rate again. All right, and so as both of these directions get higher, that equals dollar signs. All right, so your boss can't go to a ski chalet as many times as you might want to. But if we start with this untreated case here, in which we have just the silicon nitride by itself, you see it's got this viscosity at this particular shear rate. All right, and that higher viscosity is harder to process. Okay, but we take a little bit of this Z6020, whatever that might be, and we add that to the surface, and then the viscosity at that particular shear rate drops by an order of magnitude. All right, and over the course of continuous plant operation, that can be $1 million a month in terms of energy costs. So if you have these 1,000-gallon tanks, and you're making a lot of these things, that what appears to be a small drop, maybe, I mean, it's a log drop, so it's an order of magnitude, is a big drop in the cost of the process. It's a big drop in the wear on the machinery. It's a big drop in energy involved in the process. And so what is often true is that this Z6020 will cost more than the polyethylene does. All right, so a little bit of 1.7 is more than 90% polyethylene. All right, and that's because these guys know that what they make is really important, and people are willing to pay top dollar for it to get this effect on viscosity and decrease the cost of the process. Any questions about that? And you have other examples here as well. But so, a small amount of this on the surface has big effects in terms of the process. All right, and then we have various binders. Thermoplastic, which are the most important ones. Their hardening is reversible by going above or below the TM of that polymer. And so we have some examples here of high melt index polyethylene, low melt index polyethylene, polystyrene, ethyl vinyl alcohol. A lot of things that you guys are familiar from polymers: polyethylene, polystyrene, nylon. This temperature melting is how we change the mechanical properties. They can be either crystalline or glassy, depends on what you want to do. Even PVC has been used, which strikes me as weird, but it has been used. And so these are kind of the workhorses outside of the polymers themselves. We also have waxes, and I mentioned this last time. Waxes are kind of what they sound like. It's a low molecular weight polymer chain. So like floor wax or car wax is in that range, something that is easily deformed and in many cases is made of natural materials. And so there are formulations out there that involve beeswax, believe it or not. All right, so apparently you can use beeswax to make ceramics. 4 main classes: paraffin, which is beeswax, microcrystalline, synthetic hydrocarbon, and oxidized polyethylene. They can have a lack of plasticity due to their low molecular weights. All right, so they're cheap, they take up space, but you heat them up, it tends to slump the part because they're waxes. It's what they do. And so this narrow melting range can, if you're trying to remove it, if the strength changes suddenly because they've suddenly melted, that means that the part has suddenly gotten weaker. And so some examples here of different types of materials. BASF, that should be a name that's familiar to you guys. You have commercials out all the time. These polymers that have been used. And there's also thermosets. So you may not want a thermoplastic. You may want something that chemically reacts, like the epoxies we talked about. Those thermally react with each other and make three-dimensional structures. They tend to be brittle. Because of the cross-linking, you see a huge increase in strength. And so if you have a part that you're worried about in terms of its slumping, especially a larger part, you might want to use this to give it strength. Downside is it becomes more brittle, but you know, if you tell your guys in the plant to be careful, don't drop this on the floor, then you can get away with it. And you can change this by filling around the structures and either inhibit or promote the reaction between these different parts. And you can delay curing at room temperature so that it stays strong. But at elevated temperature, you can cause curing to occur, which is where you want it to become strong after it's already inside the furnace, which is kind of a neat thing if you can make it happen. All right, and this is just one example that I'm not going to go into, but phenol formaldehyde involving this reaction. Epoxies, we talked about that, so that's something that we see in the grocery store. Or bathtub caulk. Anybody ever work with bathtub caulk? And you put it on surface and you smell this vinegar coming off of it. That's the acetic acid. It's a byproduct of the reaction between the different components in the bathtub caulk. That's where that smell comes from. And it means that things are curing, that the reaction between chains is occurring. Polyesters, short-chain polymers, and then allyls as well. You know, again, there's a whole bunch of these things out there that utilized in this context. Water-soluble binders. I'm going to mention this mainly because it's got a lot of history. And this is what Battelle across the street did a whole bunch of work in this area. The thought was, because of this issue with the Hamburger constant that I mentioned before, that we'd have to use water to make these things, to injection mold these batches. And so they spent literally decades working on these water-based batches and they were eventually displaced by just heating up polymers. But these are primarily based on cellulose, and again, if you dig into the history, you'll see this. And these are, I mean, there's still some people who use them, but they've largely been displaced. So hydroxypropyl or hydroxyethyl cellulose, again, a naturally derived material that's cheap, and you're going to burn it up anyway. You can make these things gel by controlling the temperature. As temperature increases, molecules gradually lose their water of hydration and decrease in viscosity. So that means it's a reversible process. And the goal here is to supply strength to the as-molded part. So the trick was you'd start with this stuff, and so you'd mix the heck out of it with whatever shearing systems you're using, and then you'd form the part, and you'd heat it. And this is happening after it's got that total knee shape, for example. And you get this gelation temperature. And then because it had gelled, it had reacted, then the viscosity as well as the strength would shoot way up. And so it would suddenly get very strong and keep getting strong. And then what you do is you break open the mold and take it out. And then you have a high strength part if you interrupt this process at the right point. And this was a strategy that they used and pursued for a number of years, probably longer than they should have. But anyway, so there are water-soluble versions of these, but you know, as I've said, they're not used that much anymore. All right, so one of the things we did mention way back at the beginning are plasticizers. And so those of you from polymers will remember plasticizers. And here they do the same thing. They help plasticize this otherwise more brittle polymer phase. And so these are shorter chain polymers that have specific chemical structures that enable the overall binder to become softer. All right, and so that is something that is important to us because we don't want a really brittle part that can easily fracture before it even goes into the furnace, for example. Okay, and so we have the same definition in both ceramic injection molding and plastics. And so plasticizers make things softer, they make things more ductile, they make them easier to handle without causing fracture. They go in between the molecules of the polymer to enable chain-chain motion, which is what's necessary to make polymer chains move past each other. They must be compatible with the polymer, so they have to like each other. All right, so they typically tend to be the same type of structure. So if you have a polyethylene batch, then you have a short-chain polyethylene plasticizer with some type of chemical functionality on it, for example. All right, so there's good compatibility. And it must be capable of being retained by the mixture. You don't want it to evaporate, all right, while it's sitting there on the faculty floor. And there's a whole bunch of things that are obvious. Paraffin wax for polyethylene binder, waxes act as this, and a whole bunch of other organics as well. And so this is that minor component that gives us the mechanical durability in the part that's necessary in order to move it around and put it inside the furnace and so forth. And so that's one of the roles that plasticizers play. So how do we put all these things together? And as I mentioned, it's called trial and error, or process and error, depending on where you come from. And this is one example of what people have done, and there's whole books written on these things. There's books of these ternaries. You turn a page, it's a different ternary. You have butyl stearate, you have AC400. Butyl stearate is a plasticizer, all right, what we just mentioned. And then there's also, interestingly in this one, castor oil, which is acting as a processing aid. So this is a low molecular weight oil, but it has functional groups that will attach it to the aluminum oxide, if that's your processing, and then have a polymer chain that comes off the surface. And then we have the plasticizer, the butyl stearate, which makes everything softer, and then this ethyl vinyl alcohol, which is the AC400, and that's the workhorse polymer, the high molecular weight polymer. And you mix all these things together, and then you do a whole bunch of work to figure out when they are compatible or incompatible. All right, meaning that if it's compatible, it makes a thin material, meaning that the viscosity can be moved inside of a mold. Something that's stiff or very stiff might not be so readily injectable. And then you have, worst case, the incompatible, where they phase separate from each other, which is bad. We don't want them to phase separate. We want something that acts in a compatible way with a low enough viscosity that we can injection mold it. All right. And again, as I said before, they didn't open up the supercomputer and calculate this stuff. It's all by trial and error. All right. Even now, we can't use computers to predict this. And so industry as a whole is characterized by a lot of these ternaries, where they found something that works, and God help you if you deviate away from that, because it makes life difficult for everyone when you do that. All right, so, and these involve various mixtures of homopolymers or copolymers of various kinds that can be used to make this overall system work. These are just some examples of commercial products that are sold. Okay, any questions about that? I know it's a lot, but I just wanted to give you an idea of why we do what we do, and also some idea of how bloody complicated it is as well. Any questions? All right, if not, I will see you guys on Friday, right?
Yep.
Okay, all right.